you're going to show the experimental determination. For experiment 3, you're going to show the volumes and the temperatures. And then you're going to do, say, a theoretical calculation, which is the calculated volume of air at T2, so the cold volume here. You'll take the hot volume, and then you'll predict what the volume should have contracted to when you lower the temperature, and then compare it to the experimental. And then the percent error here, what we do is we take the experimental, which is V2, minus the theoretical. The theoretical is this calculated volume. So the experimental minus the theoretical divided by the theoretical times 100%. And so that's the percent error that we have here. In this area, you show represented calculations. You don't have to, we did 2 sets, so you can just pick one and just show the setup there. Or you can put both calculations here for trial 1 and trial 2. But typically, what I want to see is just the equation you used and the numbers set up. All right. In this case, what we're going to do is we're going to calculate the temperature correction here. So if we use the equation in terms of degrees C, this is just a rewriting of Charles' law, the ratio of temperatures and the ratio of volume. There's got to be a temperature correction to the degrees C, so we're going to calculate what the temperature correction is. You already know what it is, because when we use equations like this, you can't use the Celsius temperature, you have to use the Kelvin temperature. And so when we convert Celsius to Kelvin, what do we add? We add 270, close, 273. Let me do something. 5 if you want to be more precise. And so what we're going to do is we're going to just go ahead and do this using Celsius and then calculate what X should be, because we know what the temperatures are in Celsius. We know what the volumes are, the experimental volumes. You're going to use experimental volumes here. And then we should calculate X from trial 1. See, is it close to 273? That's the expected value of X. And then trial 2, did we get close to 273? So that's one way we're going to see 273. The other way is we're going to make this graph here. And so in a graph we want a title. This is a graphical determination of absolute zero. Here we have the the x-axis and the y-axis. Y-axis is volume in milliliters. The x-axis is temperature in degrees C. So our first temperature was about 100 degrees C, a little higher maybe depending on your thermometer. And the volume is the total volume here. So we put 1 point in there. When we make a point, you need to make it clearly visible. So what people do for making this, they'll put an X here and a circle. The X would intersect right at the point, and then circle it so it's more visible. Or some other means, a dot and then circle it. But an X is good because you're going to draw a line through it. And so we need to make the point clearly visible here. And then we cooled it down. So it went down close to room temperature. So there's around 25 or so. There's going to be another spot point here. And then we assume it's a straight line relationship. So we're going to have a point here and a point here. And then we're going to draw a line. What we want to do is we want to hit the x-intercept. Hopefully the x-intercept comes at, well, we go, what's the coldest temperature we can get in degrees C? Minus 273. So we're shooting for, hopefully it goes to minus 273 or close to there. But we'll just see, because the data is the data. And sometimes there's experimental error that causes it to be way off. And so see where that intersects here, and then just make sure the points are clearly visible. So you're going to do both trials on one graph paper. So just clearly mark this line is for trial 1, this line is for trial 2, and then clearly mark where it intercepts here. And what you can do is you should be able to define it, I think, to the nearest degree. This is 250, and then we have 1, 2, 3, 4, 5 blocks. So this would be 260, 270, 280, 290, 300. So we should be able to estimate it to the nearest degree C as far as precision goes. Okay, so you'll mark the intercept here, and then you'll just mark how many degrees C it is, and mark the other intercept here, how many degrees C that is. Any questions on this? You guys have done hand plots before? Yeah. No? Yes? All right, I assume everybody's done these in math. Experiment 4, we're skipping. We're not going to do this, but this was an interesting one because you could take a hydrate and dehydrate it just by heating it up. And then by measuring how many grams the mass changed by, you can figure out how many grams of water you must have evaporated out of the solid, that is, driven or vaporized out of the solid, basically. And so if you heat it up to like 100 degrees C, you can force the water out of the crystal, dry it, weigh it, before drying and then after drying, figure out how many grams, and then convert it to moles of water. And then if we know how many grams of the salt we have, we can convert that to moles of formula units, and then we can get a mole ratio, moles of salt to moles of water. And so this is a 1 to 5 mole ratio, this is a 1 to 2 mole ratio, 1 to 10 mole ratio of salt to water. And so it's a simple experiment. It's just dehydrating a hydrate. I'd like to do it, but there are too many experiments to do. Not enough time. So we're going to do this one, experiment 5, which deals with conductivity. We'll talk about conductivity too in detail. This is a demo lab. There was also supposed to be another lab set up, but didn't get set up. I might continue with this one because this one is going to be pretty fast, I think. Take too much time. But we have a light bulb set up here, and the wire isn't connected. So we have this. This black wire. This black wire is called the hot wire. This white wire is called the neutral wire. And so electricity wants to flow through it, but this black wire is connected to this piece of copper. This white wire is connected to this piece of copper here, but it's not connected to one another. So it's like the wire was cut right here. We call it an open circuit there. Electricity is what? What is electricity? What would you tell somebody what electricity is?
Dangerous.
It's dangerous, yeah. We don't want to electrocute ourselves, which is pretty easy to do with this.
Isn't electromagnetic force stronger than gravity?
Yeah. Electrical forces are stronger than gravity. Gravity can be very strong, though, too, but you have massive bodies that would account for that. So electrical forces are what were most important in chemistry. But what is electricity? I forgot my camera. I have a little webcam. I could have done this. There's a flow of what? Electrons, right? And electrons are charged particles, negatively charged particles. And so these flow of electrons. So the electrons are trying to flow. through the circuit, but they can't because there's a big gap here. And so if I plug this in, we're not going to see any light come through the light bulb. Let me plug this in here.
Positive?
Hmm?
Is that like the positive?
Yeah, right. There's one end that's kind of positive, another end. This is an alternating current, but
The electron has electricity reference of metal or something? So it can connect to that.
yeah. Well, we need to connect the wire or the circuit or the copper because metals. One of the properties of metals is they have good electrical conductivity. What good electrical conductivity means is that the electrons can move through the wire. Here, let me talk about conductivity first. So electrons, if I have a wire, there are different ways that people think, and conceptually, some people will say maybe this is the best way to think about it. Other people say, fields, electric fields, which we'll talk about, but normally we just think of flow of electrons. In metals, the electrons are loosely held. Whereas in things like insulators, like glass, the electrons are tightly held because we have electrons in all matter that we're interested in. And so for metals, we have what we call low resistance to flow, good conductivity. And so metals have good or excellent conductivity. Conductivity means this ability to flow, and there's low resistance to the flow. That is, we can make higher resistance. So for example, when the metal gets hot, what happens to the atoms in a metal if they get hot? There's more kinetic energy, which means they do what more? They move more. What kind of movement? They don't translate because unless it's molten. If it were molten metal, it would translate. Mercury can translate because mercury is a liquid. Liquids have translational motion. It's vibrational. So they vibrate. And those vibrations are going to interfere. So the hotter the metal gets, the more resistance there is because the atoms are vibrating more. The colder the metal gets, the less vibration and the easier it is to flow. And so they have something called superconductivity where there's zero resistance. And a lot of metals will display superconductivity if you get them cold enough, that the vibrations become so minimal that the electrons have a free path to go through. People are looking at this because there's a lot of energy that's lost in transmission of electricity. So they're saying, okay, if you transmit, let's say if you transmit from the Sahara Desert, there's lots of sun, so people are thinking they're going to put solar panels out in the Sahara Desert and then try to transmit the electricity all the way to Europe, because there's not as much sun in Europe. But the losses are tremendous due to the resistance. And so there's a lot of energy that's lost pushing the electrons through. It would just be like a crowded room. If you're trying to push through a crowded room, there's a lot of resistance, but in an empty room, there's very little resistance. You just walk right through. Right? So, basically, metals have very loosely held electrons. So going back to this, there are different ways that we can complete the circuit. We're going to try to complete the circuit being the wire there, using different things. So if we use iron, solid iron, what do you think is going to happen? It's going to work. We have the solid iron. So this is steel, which is mostly iron. Steel's an alloy, like stainless steel, but it isn't as corrosion resistant. And so it's a lot cheaper. Copper is pretty corrosion resistant, but when you look at this copper, it's been pretty well corroded. We could clean it off. So I'm not going to touch the metal here, I'll just touch the wood. Wood has tightly held electrons. And so wood is not a very good conductor of electricity. It doesn't, it could be a tiny piece of metal, it's just going to get hot. And if you have a tiny piece of metal and it gets too hot, it'll melt, basically. If there's danger like this, you don't want to touch that. If you touch those, you could complete the circuit yourself. And you don't want the electricity to flow through you because they say, I don't know, in physics they say it's not the voltage that kills you, it's the current that kills you. It's the flow of the electrons that will kill you. If you have a large flow of electrons through your body, it's going to kill you. So I'm going to take extra precautions to make sure I don't electrocute myself. Here. Well, air is not a good conductor of electricity because there's an air gap here, and the electrons aren't flowing through the air gap. I can get the electrons to flow through the air gap. Do you know how? How electrons can flow through the air? You've seen it before. Everybody's seen lightning, right? Those are electrons flowing through air, but what do you need in order to create lightning? Well, it depends on how big the gap is. For a gap this size, you'd probably need like a couple of thousand volts. Do I have a couple of thousand volts out of this plug? No. You know how many volts I had? 120, maybe peak, 130, maybe. Probably less than 130 peak. 120 average, and then it goes up and down because of the way we have the electricity. Maybe 115, 120 average. We call it the average RMS, root mean squared average.
How many volts are using the plugs in the outlets?
120 RMS. The peak voltage could be a little higher. RMS is about like 0.67, so maybe another 10% on top of that, maybe up to 130 maybe max. Peak. It fluctuates like this because we have alternating current. It's not like like 240. We also have 240 or 208 in some of the plugs. So for electric ovens and electric dryers and electric washers, those are 240, most of them. Some are 208, depends on what region of the country you live, But 240 and 208, that's a lot higher voltage. That will create quite a shock. I've been shocked by 120. I survived, but I haven't been shocked by 240. That would be more serious. I know people who've been shocked by 240 in other countries. 230 is common in Europe and elsewhere, Asia. But anyway, this is not enough voltage to transport electrons in the air gap here. And so what we could use, we could use a piece of steel and see. A piece of steel, what do you think is going to happen? Well, we have electrons that want to go from one negative. One of these is charged negative, the other's charged positive. So the electrons want to flow from the negative to the positive. And so let's try this and see what happens here. So I'll connect it, and that creates a circuit. And so iron like this, electrons can flow easily through the iron because of this structure of the iron. Metals have what we call a metallic structure. I might as well talk about that since we're talking about, what are we talking about? We're talking about composition, structure, and properties. So somebody was asking me about structure the other day. I don't know if it's in this class or the other class. But metals, the structure of metals is we have a whole bunch of atoms packed together. here. And very simplified. This is taking the quantum mechanics and simplifying it to like a cartoon level so that people could better understand it. But the cartoon level picture of this is, we call this the electron C model. And the quantum mechanics of this is called band theory. Band theory is just an application of quantum mechanics to metals, semiconductors, and insulators. What defines a metal? What defines a metal is excellent conductivity. Conductivity is given this symbol, sigma, usually, and the units for this are like Siemens, as far, you know, Siemens, the semiconductor firm, that would be, and the resistance is given this symbol, omega, and the units for omega are ohms. And so what we see for metals is we see high conductivity. For semiconductors, we see medium conductivity, or low. Actually low. For insulators, we see pretty much negligible conductivity or no conductivity. It's not zero, but you say, I shouldn't say no, I should say negligible. So conductivity, you don't have to know this equation. This is the equation for conductivity. Depends on three things. Depends on something called mu, n, and e, or z. Maybe let me change that to z. The symbols vary depending on what book you use. So this is the conductivity. So the standard is like copper and gold. Copper and gold have really excellent conductivity. Mu is this symbol here, and that represents mobility. So we were just talking about mobility. At high temperatures, what happens to the mobility? It decreases. At low temperatures, the mobility increases. And so that's going to impact the conductivity here, correct? You know what Z is? Z represents the charge. So for example, the electron has a charge of -1. And N represents the number. So we need a charge carrier. This is called a charge carrier. A charge carrier like an electron, because we need something to go from the negative electrode, which is that chunk of copper, to the positive electrode, which is the other chunk of copper. And so we're going to have these electrons here. And the electrons have to have mobility. They have to be able to move through the metal. And basically, this is pretty like an empty room, kind of. It's like an empty room, so we say that it's well, let me try to change that. Maybe I'll do it in blue. light blue. Goodness. So this is the C. The atoms are like fixed Pierre pilings in the C. So people think, the nucleus is charged positive, but the nucleus doesn't have mobility. The nucleus is stuck in the middle of these atoms, and it's not mobile. Doesn't have translational motion. And so in the electron C model, the nucleus and the atom is like what they say is a Pierre piling, and the electrons are like the ocean. So the electrons can flow around the Pierre pilings here. And so this is the metallic structure. It forms a crystal lattice of atoms. These aren't ions, these are atoms, but the electrons are loosely held. And there are plenty of electrons there, of the loosely held electrons. So again, it gives good, look how bright that bulb is. It gives good conductivity. I forgot to do this one thing. Let's see if I can still do it. All right, let's take a look at the next thing we're looking at. Distilled water. What's the difference between distilled water and deionized water? We don't have distilled water. You know what we have? We have deionized water. The difference is how it's purified. How is distilled water purified? By distillation. And what's involved in distillation? No, reverse osmosis is our deionized water. Actually, our deionized isn't even that. I don't have any distilled water. Distilled water, you boil it off, and then you capture the vapor. You guys remember the distillation apparatus?
It goes away and it slides down.
And yeah, it goes into the condenser tube. The condenser tube's cooled by cold water, and then you collect it. And so distilled water is good, better, I think, than our deionized water, but this one, So if you take organic chemistry, you'll be setting something like this up here. We can just boil water here, and then collect it in the condenser tube, and then we'll have distilled water collecting over here. Any impurities should be left over here. Or if they're volatile impurities, those will come off first before the distilled water. So you just collect fractions, depending on.
And volatile impurities don't make it.
The volatile impurities do. So what you do is you collect those first, and then remove that, and then put another flask, collection flask here, and then we'll collect those. And so the volatile impurities.
How do you volatile?
You find out by the temperature. There's a thermometer stuck in here. And so if you have volatile impurities, they're going to come off before 100 degrees. When you hit 100 degrees on the thermometer, then you start collecting, because that's going to be your water. And so you use the boiling point to separate the components of the mixture. And then once you do that, then you should be collecting pure. You know, as long as the temperature stays stable, the boiling point's one of the properties, physical properties of substances that use. So we have deionized water, and our deionized water removes the ions using a different technique. The tap water passes through what are called ion exchange columns, and these ion exchange columns kind of absorb the ions in there. And so it's also pretty good, the quality of this. You know how, I'll tell you how we measure the quality of our water in just a second. And so I have my deionized water here. And then I'm going to use this to complete the circuit. What do you think? Is it going to light up the bulb? No? Yes? Let's see what happens here. Now, let me turn off the light. Maybe it's very dim. Do you see any light? No, maybe it stopped working. Let me check. Make sure it's still working. Yeah, it's still working. So what would you conclude based on that observation? Deionized water does not conduct electricity. So if that's the case, what should we classify deionized water as? A conductor? Well, we classify things in three categories. Conductor, you know, a metallic conductor, we could say. A semiconductor, or an insulator. And so conductors are going to have high conductivity. But it doesn't have to be metallic, because there are other things that have good conductivity but aren't metals. Do you know what has good conductivity but isn't a metal?
Regular water. Minerals and stuff in it.
Well, yeah. Let me see. I'm going to sacrifice one of these pencils, maybe. Do you know graphite is a good conductor of electricity? Yeah, from one side. However, the graphite in pencils consists of a whole bunch of little crystals, and those little crystals can put like a maze-like path for the electrons to go through, and they'll conduct electricity. I don't have a piece of graphite, unfortunately. That's big enough. Let me see if I can make one. Pause for. Does water have good mobility?
Yes.
Liquid water does. How about solid water? Does solid water have good mobility? No. Mobility is we need translational motion. So liquid water has high mobility. Are there a large number of water molecules in a glass?
Yes.
Yeah. I mean, there's so many, you couldn't count it. Even in one drop of water, if you tried to count the number of water molecules, one by one in one drop of water, you'd die before you'd be successful. You know, there's just too many to count. And so it has a high number, high N. But why is the conductivity so poor?
Because it's charged bad.
Yeah, because the charge. What is the charge on a water molecule?
Neutral.
The charge is 0. And therefore, what do we expect for the conductivity?
Insulator.
Yeah, it should be an insulator. So water, pure, this is pure water, by the way. Should be an insulator. I shouldn't say, or close to 0. We'll learn later that there are some charged species in water, even in pure water at 25 degrees C. But anyway, it's an insulator. This is how we can tell the purity of our water. The way we check our water purity is we stick a multimeter in the water. Actually, there's a multimeter set up here. And we measure the resistance of the water. The resistance of the water should be mega ohm. If we have mega ohm resistant water, then we know it's pure. If the resistance of the water goes down, then we know we need to change our ion exchange resin, which is like the sponge. Is tap water pure? No, actually, I've used the wrong one. This is supposed to be deionized water. Let me rinse this one out. So let's go with tap water here and see what happens. Will it conduct electricity? Tap water conducts electricity. Keep electronics away from tap water. You can electrocute yourself. Yeah. Is the bulb very bright? No. It's not very bright because does the water taste very salty to you, tap water? No. It has some minerals in there, but not that much.
If it's like salt water, it'd be a lot brighter, right?
If this were salt water from the ocean, it'd be a lot brighter.
So that means like more minerals?
Yeah, the more minerals you have in there, the brighter it's going to be. We don't. You don't need more minerals. I mean, this tap water's already got a lot of minerals in there. So tap water has dissolved minerals in here. And what happens when the minerals become dissolved in here? It makes ions. So one of the things that tap water has is it has sodium in. I think it should have sodium in there. You can do a quick test for that. Look at my matches. Matches disappear. What types of ions do you find in water? Do you know? Sodium. Sodium ions are everywhere.
And they're positive.
Hmm?
They're positive.
They're positive. So the charge carrier can be electrons or it could be ions. Electrons will flow from the negative to the positive. Cations, which are the positive ions, will flow from the positive to the negative. And therefore, the negative electrode and the positive electrode have another name for them. If the cations flow to the negative electrode, we call that the cathode because the cations flow to it. The anions, let's say there's chloride in here too. That's a pretty good guess. The chlorides will flow the other way. And so these will go to the cathode, go to cathode. The other ones, these go to the anode. And so we give names. So we have two electrodes here. One's positive, the other's negative. So rather than calling it positive and negative, we call it cathode and anode because of the flow. The cations will go to the cathode, the anions will flow to the anode, and then you can figure out what the charge is if you want. And so both of these will conduct electricity because the conduction of electricity is all we need is a charged particle, and we need some number of them. In tap water, there's enough to dimly light the bulb. And so it was a, what would you say the conductivity was?
Tap water?
Of tap water? Yeah, medium, or we'll just call it moderate conductor of electricity. There are other ions in tap water. I don't know what those are. Those other ions. But the concentration's not terribly high compared to like seawater. Do you drink seawater? Can you drink it? It's too salty, right? Uh-huh.
So in the example of the label right here, if we had sodium into water, it would be going toward yellow.
Well, the yellow, this yellow is just an insulator jacket. There's a white and a black. And so you don't have to worry about it. If we had sodium in there, it would be going to the negative. Now the thing with alternating current is it flips. And so the electrons are moving like this. Yeah, so if this were what we call direct current, then the cations would be going to, and we use a different color coding system for that. The cations would be going to the black or the negative terminal, and the anions would be going to the red or the positive terminal. Like a car, exactly. Like a car. A car is two conductors. If you look at a car battery, the external circuit is electrons. Inside the battery, there's what we call an internal circuit. The internal circuit are ions traveling. So you have cations and anions inside the battery traveling to the anions going to the red and the cations going to the black terminal of the battery inside the battery.
I guess that motion that creates the force or the power to light it up.
What is the? It's just what you're doing is you're charging one side, forcing electrons to go to one side using a power supply. The power supply could be a battery, but we have a power supply here, and so having an imbalance of charge will cause it to flow. I mean, the force, we have to use some electromotive force to push the electrons. In other words, electrical force. So the dissolved minerals, they have charge, they have mobility, and they have numbers. Their numbers aren't so big, but the charge is good and the mobility is good. The number is small, therefore it's moderate. But tap water can still kill you. Let's go to solid sodium chloride. The sodium we have up here, we label AQ. AQ stands for aqueous. What does aqueous mean?
Dissolved in water.
Dissolved in water. However, sodium chloride normally is a salt. You know, you can get it like a salt packet at McDonald's or wherever. And it's a solid. And it consists of a lattice like this, where we have the sodium ion and the chloride. Chloride's a lot bigger. And what do we call this structure? A lattice type structure, ionic lattice. In an ionic lattice, if you're a sodium, do you want to just bond with one chloride, or do you want to try to bond it with as many chlorides as possible? If you're a sodium here, your charge is positive. Do you want just one negative, or do you want lots of negatives around you? Just one? What would limit it to just one? Because think about Coulomb's law. If another negative comes along here, you know, this is a pair. What would the other negative do? Ignore this? Move on? Or would it be attracted to the positive charge here? It would be attracted. And then if another negative came along, what would happen here? Again, it would be attracted. And in fact, each positive wants to surround itself with as many negatives as possible, because that is favorable. So how many negatives can you fit around here? Can you count them?
Let's say 4.
In 3 dimensions. In 2 dimensions, it would be 4. 6. It would be 6. Do you see it?
Yes.
So this is why sodium chloride doesn't form molecules. Sodium chloride doesn't form molecules because each sodium wants to bond with 6 chlorides. And each chloride wants to bond with how many sodiums?
1.
No, as many as it can. 1, 2, 3, 4,
6 as well.
6 as well. 5, 6. Each chloride wants to bond with 6 sodiums. And so the ratio is a 6-to-6 ratio. In other words, it's a 1-to-1 ratio. Empirically, it's a 1-to-1 ratio. And so this is the lattice structure. Versus a molecular structure. If I have an oxygen here, does that oxygen want to bond with as many hydrogens as we can fit around it? And then each hydrogen wants to bond with as many oxygens as we have? Do we form something like this? The answer is no, we don't. What we form is we form discrete molecules. Sometimes we can cluster these molecules. Sometimes they'll cluster. Together. But it occurs as a single unit. And so each oxygen only wants 2 hydrogens, and that's it. And so here in a lattice like this, we have the empirical unit, And the empirical unit is not unique. Like, for example, this is an empirical unit here. This is an empirical unit. There are a bunch of empirical units in here. Over here, this is a molecular unit. And that is unique. So let's try solid sodium chloride. This is just table salt. What do you think? Is it going to conduct electricity or not?
Yes.
Johan, what did you say?
I said not by itself.
Not by itself. Why did you say yes?
Everybody Johan said
Why do you say it's not going to conduct?
I just feel like just salt itself can't make electricity without a conductor involved in it, I guess you could say.
Okay.
Not for the conduct because it has like a neutral charge.
Well, sodium chloride does have a neutral charge, but it's made up of sodium ions, which are positive, and chloride ions, which are negative. And sodium chloride, we just saw, did conduct, because in tap water we have sodium ions and chloride ions that can conduct electricity.
I guess the difference is that was aqueous, this is just a solid.
That's one difference. And so, what does that mean? You got to talk more mathematically. What does that mean mathematically here?
Mobility is just vibrational.
Mobility is only vibrational. Is there translational mobility in solids? No. And so the mobility should be?
Lower.
This mobility is only translational. When I talk about mobility here, we're just talking about translational. We don't care about vibrational or
The
rotational.
charge is the same in the number. Would the number be increased?
The number is huge. We have a huge number of ions in here. And the charge is plus and negative. We have plus ions and negative ions. But what about the translational mobility of solids?
Doesn't exist.
There's no translational mobility. If there's no translational mobility, what does that do to this equation?
It's a pulse.
Yeah, it makes the conductivity 0, which means this should be a
It's like
insulator. So we're going to test it and see. Does it conduct electricity? No. It's an insulator. I'm sorry?
Could you just repeat why it's an insulator?
It's an insulator because its conductivity is 0. Its conductivity is 0 because it has no mobility, mu. So we plug that into the conductivity equation. The conductivity equation gives us 0 conductivity, which is the insulator.
the other thing is with water goes in. You okay?
Yeah. So if I add water to this, you know what the water does? The water pulls apart the lattice structure. And so water molecules come in here and breaks apart the lattice. And actually, that's what we're going to do next. So.
Wait, I think I mentioned this in the past before, where like the water goes in between. Is that correct?
That's for hydrates. Sodium chloride, we say, is soluble in water.
Yes.
Now, what happens is when we answer this question in two ways. So if we take solid sodium chloride and we add water, we can make aqueous sodium chloride. And so the sodium chloride dissolves. But what happens when it dissolves? What happens when it dissolves is it breaks apart into ions. And so the first arrow represents what we call solubility. It's soluble. S. We have other terms for this. We have things that are slightly soluble, SS, and insoluble. In this case, it's soluble versus slightly soluble. SS versus insoluble, which gets the I. The second step to this we call electrolyte properties. And it breaks up into ions. So as far as electrolyte goes, we have three categories of electrolytes. We have strong. Strong dissociate into ions. Near complete or complete. So I'll just say near complete dissociation. So the entire lattice is torn apart. In this case. Then we have weak. Weak electrolytes have partial dissociation. And then finally we have non-electrolytes have no dissociation into ions. When I'm talking about dissociation, I'm talking about into ions. And so what's happening here is the water molecules are coming along. We have our salt lattice here. And the water molecules come along and then they collide with the lattice. And the water molecules themselves have a charge associated with them, so so the oxygens are tugging, the oxygen end of water is tugging on the sodium ions, and the hydrogen end of water is tugging on the chloride, and eventually it breaks apart the lattice. And when it breaks apart the lattice, we end up with the free ions. And so we'll have a sodium ion like this, but it's not completely free because that sodium ion has a charge associated with it. And the sodium ions are going to be what we call hydrated or solvated by water molecules. So these water molecules will surround the sodium ions. This. And what that does is it helps stabilize the charge. This is called a hydrated or solvated ion. Hydrated because it's water. Solvated because water is what we call the solvent in this particular case. And these ions are still mobile. They can move around. And so they have translational mobility now. And the chlorides are the same thing. The chlorides, however, are going to be surrounded by the hydrogen end. of the waters. And that's going to stabilize the negative charge. We like charge neutrality. When you have separation of charge, it becomes unstable. It becomes like a high voltage. High voltage situations aren't so stable. Because if you start separating more and more charge, you put more negative charge on one pole and more positive charge on the other pole, eventually you're going to get a lightning bolt, a spark. You probably walked across a carpet, you know, in socks or shoes, and then grab the door handle. Have you ever been shocked? Yeah. Yeah, it's unstable. We don't like that separation of charge, so it's going to discharge to restabilize things. And so these are hydrated solvated ions. And these have translational mobility. And they have charge. And so we have positive charge over here, we have negative charge over here.
Could you explain how transitional works now? Because the electrons can go through them. Translation now is because the electrons can go through them.
No, electrons don't go through anything. What's happening are the ions are going through. And so let's draw some electrodes here. So we could use a power supply, and what the power supply does is it pumps electrons to one of the copper pieces here. It pumps electrons to this side. And then what we're going to have is we're going to have our cations and anions in here. So we have our positive sodium ion and our negative chloride ion. And we got a bunch of these in here. And then we see translational motion's not electrons conducting. The electrons are not the charge carrier. What is the charge carrier here? It's the ions. And so what's conducting electricity are not electrons. What's conducting electricity are the charged ions. And the mobility comes here. The negative ions will go to the anode. And the positive ions will go to the actually we don't have to worry about the names here. Just the negative ions will go to the positive electrode, the positive ion should go to the negative electrode, and that conducts electricity.
And if they're packed together, they would be able to go through, or
I'm sorry?
if it wasn't an aqueous, it would be solid,
Uh-huh.
you'd be able to conduct electricity.
If it's a solid, there has to be a pathway, a tunnel that the ions can travel through. There are some solids that have tunnels that ions can go through. You know, those are called the. People are looking at this for batteries. I talked about superconductors. Do you remember what superconductors are?
It's like when metals have zero resistance.
Yeah. It's like an empty room. It's clean path. So there's things that are called superionic conductors. Superionic conductors is they'll have a clean path through the structure here. Let's see if this one has. So this is a superionic conductor, which means there's very little resistance for the ions. There's very little resistance in water, but the problem with water is it limits the temperature. What's the maximum temperature you can have for water? About 100 degrees Celsius. A lot of batteries need to operate at higher temperatures than 100 degrees. So if you have a battery that needs to operate, like, you know, when I go to charge the Tesla battery preheats for optimum charging. You know, the temperature that it preheats to is a lot hotter than 100 degrees C. They can't use water. In car batteries, we use water, but your car battery, is it going to get over 100 degrees C? If it did, you're going to have big trouble because you're going to boil off all the water and your battery is going to go dead. But for battery applications, we need things that conduct ions that are solid.
So that way you need like really strong, like metals with high boiling points.
You need a lot of things, but some batteries want high temperature so they can get molten metals. There's a molten sodium ion battery, which is supposed to be very efficient, but it has an operating temperature that's kind of high, which makes it expensive. Because in order to heat it, you have to use electricity or some other power, and so the efficiency is going down. And so you see these channels here? The ions can flow freely through the channels, so like empty hallways kind of thing. And so even though you have a solid building, you have empty hallways that the ions can flow through, rather than the ocean. You know, if you're in the ocean, then the ions can flow through. So all this stuff is really important for batteries. We call these electrolytes are a really important topic in batteries. Electrolytes are things that can conduct using ions.
Now
those type of
water
things.
powered cars are very difficult to make.
I'm sorry?
Water powered cars, not water.
The water powered cars are not water powered. The water they're using as a source for making the fuel. So some of these cars, well, it depends on what water powered car you have. It's like, okay, I want to make a CO2 powered fire. Are you going to be able to make a CO2 powered fire? In other words, I want to use CO2 as my fuel. Can you use CO2 as a fuel? No, because that's the waste product. The fuel is already spent. But what you can do is you can convert the CO2 into a fuel. Well, the water is already spent. Water is a product of combustion. When we combust the methane, what forms? CO2 and water. If we could get more power out of water, shouldn't we get more flame out of the water? In other words, can you burn water? Does water burn? Under extreme conditions, you could potentially burn water, but that would be extreme because you'd oxidize the oxygen in water to make oxygen. That's potential. But what they're talking about, and this is what I think, what might make it feasible of having a water-powered car is using sunlight. Uses sunlight to split the water up into the elements. And so how can you convert water into its elements? You can use chemical separation techniques. One of the chemical separation techniques you can use to split water up, I showed. Does anybody remember it? When I was talking about chemical separation techniques, I showed a video. Do you guys recall that video? It was so long ago, you probably completely forgot about that video, right? It splits water into hydrogen and oxygen. Do you remember?
Is it the one where they put like the battery underneath the...
Yes. Do you remember the 9-volt battery and the beaker of water, or you completely forgot it?
They put like the pin on the bottom of the...
Yeah, you don't even need the pin. People just will drop a whole 9-volt battery in water. I was trying to find that particular video, but I couldn't find it, and they keep changing the links for this. So. There's one where they just drop the entire battery in water. That video's the one I wanted. I didn't want the pins. That was too fancy. I wanted just the battery. Like this. This might be it. Oh yeah. Do you see that? Except this one isn't as clear. They need salt in there because batteries have two circuits. They have the external circuit and the internal circuit, but the salt will help speed things up. And so the salt isn't for the battery itself. The battery inside has stuff and that will help complete the circuit. We'll talk about batteries in chapter 19. But the salt, if you don't use salt, it goes extremely slow. The salt is there to speed things up because it helps neutralize the charge quicker. The salt acts as an electrolyte. And so we just take table salt here. You could do this at home, but it's wasting a 9-volt battery. 9-volt batteries are getting expensive now. You could try it without salt. It's just super slow. You dump some salt in there. You create some ions. The saltier the water, the faster this will work. And then do you know which one's generating the hydrogen and which one's generating the oxygen? This is the positive, this is the negative. Actually, bubbles should be forming on this one too. I don't know. This is corroded, I think, or something. It's weird. There should be bubbles coming out of here too.
That's probably the left one's the oxygen.
Left one's the oxygen, right one's the hydrogen. Let's get one that has it better. Maybe this one is better. This is creating some kind of vortex. This is too long. So salt water again. That's why it looks so. So here they're producing. Here you can see the bubbles forming. They got the salt, sodium chloride. It looks like they have a magnetic stir in there. Egg drop from space. Well, I haven't seen this one. World's highest egg drop. I wonder if it survived.
Oh, I've seen it.
You saw it?
Yeah.
Was it worth watching? This isn't it either. It'll take me time to find it, the good one. But anyway, we can separate water by chemical means, and then we create the fuel. The fuel would be hydrogen. Oh, this is showing graphite. This was interesting because graphite's a good conductor of electricity. Yeah. It's like a half teaspoon of salt in the shot glass. What's your question, Mike? Okay. So I was trying to cut the pencil to make it like that so I can conduct electricity using that. So graphite's not a metal, but it has excellent electrical conductivity in 2 dimensions. But the way graphite is graphite has a whole bunch of little crystals sintered together, and therefore it can conduct in 3 dimensions. And so they're using graphite electrodes rather than the stainless steel electrodes on the battery. And then you can see bubbles. Do you see bubbles forming down here? This has got to be the hydrogen here, twice as many bubbles than oxygen. We'd have half as many bubbles. We have twice as much hydrogen than oxygen. So hydrogen over here. So that's another crafty way of doing it. Here. Okay, let's take a break here and then we'll start up again. All right, so going back to the prospect of using water as a fuel. When I think about water as a fuel, I think about like ash. You know, can you build a fire with ash?
Not really. I mean, ash is, it's already, the fire's already been spent and you're left over with ash. Yeah. And so the same thing, when I think about automobiles, can you power your automobile with the exhaust coming out, the CO2 and the water? No, it's already spent. The energy's been spent. You aren't going to get much energy out of ash. However, if you split the water to make hydrogen and oxygen, then yes, you could use water as a fuel. And so there are people who are trying to split the water, but the thing is they need a voltage. You don't need 9 volts. You need, I think, about 3 volts will do it. But how are you going to generate that? And the problem with it is that it costs money to generate. I mean, 9-volt batteries aren't cheap. And if you're going to use a 9-volt battery to generate electricity, it's not going to be, or not generate electricity, excuse me, to generate hydrogen, it's not going to be the most efficient way of doing it. And so what people are trying to do is they're trying to use solar energy to generate what are called solar voltaic cells, to use those to split water and hydrogen. But the problem with solar voltaic cells for water electrolysis is that it's not very efficient. And so let's take a look. Solar voltaic cells for water electrolysis. So solar water splitting by photovoltaic wow, with efficiency over 30%. That's extremely high efficiency. I had a friend working on this. At the time, the efficiencies were like less than 10% efficiency conversion. Oh, this is way off, isn't it? Can you see my full screen? All right, because that was weird. This is an article from 2016 published in Nature. Nature is one of the premier journals in science. So usually the stuff that's published in Nature has been rigorously reviewed. That is, they get the strongest critics to try to find anything to reject the paper by. However, it's still not perfect. A whole bunch of COVID papers that were published in Nature have been retracted because it turned out to be incorrect. And so it still happens. It's been happening throughout history. Every year there are retractions. But Nature, it's very unusual for retractions to appear in Nature. In Science Mag. Science is the other one that's rigorously refereed or reviewed. Normally in a paper, how many papers are published every year? 1 million? 500,000? Some ridiculously high number. Are you going to be able to keep up with all that? No, and so what most people do is they read the abstract. The abstract should give you a short synopsis of the paper, including the key findings. And so what we do is most people just read the abstract, like 99% of the readers only read the abstract, and 1% are interested, read the rest of the paper. So the abstract should give us the whole paper in a nutshell. So let's see. Hydrogen production via electrochemical water splitting is a promising approach for storing solar energy. For this technology to be economically competitive, it is critical to develop water splitting systems with high solar to hydrogen efficiencies. Here we report a photovoltaic electrolysis system with the highest STH efficiency for any water splitting technology to date. To the best of our knowledge, our system consists of 2 polymer electrolyte membrane electrolyzers in series with 1 indium gallium phosphide. The indium gallium phosphide
is a alloy, and the ratios are adjustable, so they can adjust how much indium, gallium, and phosphorus. Sometimes they'll pinpoint the ratios by setting up an atom ratio like this for the mixture. This one's very generic, and so we don't know what the atom ratio is, but sometimes they're much more specific about the alloy by pinpointing what atomic ranges we need the ratio of the atoms to be to make it operate properly. Gallium arsenide is another semiconductor, and gallium indium, and nitrogen, arsenic, antimonide. Wow, that's an interesting alloy there. Triple junction solar cell, which produces a large enough voltage to drive both electrolyzers with no additional energy input. So they have enough voltage produced strictly from the solar. A lot of these solar cells, the voltage that they get is very small. The solar concentration is adjusted such that the maximum power point of the voltaic cell is well matched to the operating capacity of the electrolyzers to optimize the system efficiency. The system achieves a 48-hour average STH, that is solar to hydrogen efficiency of 30%. These results demonstrate the potential for cost effective. We always have to worry about losses. So this is why when I think about, like using methane in a methane combustion vehicle versus burning methane to produce electricity. The electricity has to be transported. So let's say they burn methane to produce electricity at a power plant. Electricity transported over the wires. How much energy is lost through the transport through the wire? A lot. And then how do you store it? You can't store electricity unless you have like the Tesla battery. Have you heard of the Tesla battery? You have to use the electricity as it's been generated because you can't save it in your wallet. You could save it in the battery, so you charge the battery. And so we need the electricity to be generated on demand. Now they're looking at batteries. They're looking at batteries for large communities, but it's not enough. So anyway, this is interesting. And so there are a lot of questions that come up in talking about this kind of stuff. Let's take a look at their calculations. Some of these calculations are ridiculous, like Tesla's calculations. Tesla on the output, if you get a Tesla car, it says, okay, you've driven this many miles or something, and it cost you this much in electricity. And then I thought, wow, I'm saving so much money. And then I looked at their calculations, because you want to see how they do the calculations. You just don't want the end number. So it said this trip cost maybe $2 in electricity. Then I looked at the calculation, and their calculation is based on 14 cents per kilowatt hour. And I thought, okay, 14 cents per kilowatt hour. Then I look at my electricity bill. My electricity bill is at 38 cents per kilowatt hour. And so it's totally off. Totally off. So don't trust the calculations until you see the conversion factors that they use. And then you can realize my cost is more than triple of what they're telling me the trip costs. But anyway, the Department of Energy has calculated the hydrogen threshold cost to be $2 to $4 per gallon of gasoline equivalent, whereas the most up-to-date reported hydrogen cost by electrolysis is $3.26 to $6.62 per gallon of gasoline equivalent. Now, this number is so much higher. Hydrogen is so expensive now, so it might make it worth it to do it photovoltaically. So this might be more economically feasible now. Let's see. Since hydrogen prices have skyrocketed. I drove by, on 190th Street, there's a hydrogen filling station there. And so I drove by the hydrogen filling station. It was, I think on Monday, and I looked, there are like 4 cars waiting to fill up their tank with hydrogen. I was just curious. So one day I want to stop by there and see how much it costs to fill up a tank. Because I was thinking that would be kind of cool to have a hydrogen-powered vehicle. But the hydrogen-powered vehicles, they don't burn it. They burn it without a flame, basically, and they produce electricity, and electricity drives the car. But let's get back to our lab here. And so salt
solid salt does not conduct electricity. Why? Because there's no, which symbol would we say?
Really?
Yeah, no mu. There's plenty of ions. N's very large. Z's fine. This is just 0 mu. But we can free it up. And so salt is soluble in water. And so what we're going to do is we're going to just add some water and dissolve. What should I use to dissolve it? Should I use tap water or should I use deionized water? Deionized water. So anything that deals with the chemistry itself, we use deionized. But for rough rinses, we use tap water just to save money. Rough rinsing and other things that don't require clean water, you could use tap. But this, we want to make sure that it's not the tap water that's conducting electricity. We want to make sure it's the, what we call the salt solution conducting electricity. So let me plug this back in here. And let's see if this is still working. Yeah, it's still working. So I'm just going to get some water, and what's going to happen? It's going to break apart the lattice, free up the ions, and then we're going to get mu. Translational mobility there. It's very bright. It's very bright because this is really salty water. I mean,
If you add more water, it's going to get dimmer.
hmm?
If you add more water, it's going to get dimmer.
No.
So if it was more water, it wouldn't be.
It's still it's going to be still very bright because I have so much salt in here. Look how much salt I got in there. This is way saltier than the ocean. If I keep adding more water and it spills out, then it will get dimmer. So it's very bright. Of course, we call salt an electrolyte, and we call it a strong electrolyte. But there are two definitions for strong electrolyte. One definition the battery people use. The battery people just care about how much. You know, this is an excellent conductor. This conducts electricity just as good as copper. Look how bright that bulb is. So if you put a copper wire here versus salt water, you can't tell the difference, can you, in the brightness? So this is metallic conductivity, we call it. Salt water has metallic conductivity. And so we say salt is a strong electrolyte. Salt is a strong electrolyte because it has strong conductivity. However, if I dilute this by adding lots of water, now it's going to go dimmer. You know, I just had way too much salt in there. But if I dilute it, I just took a little bit of the salt water. Do you see it's dimmer? Let's compare. This versus this. Do you see it's dimmer? And then I can make it dimmer still. So what I'm going to do is I'm going to pour this off and do what we call solution dilution. Just add more water. They used to say, when I was young, they used to say that the solution to pollution is dilution. Have you heard that? And so they used to dump DDT out here off Palos Verdes. Did you know that? There's like a whole bunch of 50-gallon drums of DDT out there because the solution to pollution was dilution, so dump it in the ocean and then let it dilute. But apparently you know the brown pelicans on the Channel Islands out there? You know, their eggs were getting so thin that none of them survived, and they were afraid that the brown pelicans were going to go extinct in that area because they couldn't reproduce. But there you go, dilution. So there are two definitions for a strong electrolyte. One, if you're a battery person, a strong electrolyte is a strong conductor of electricity. So concentrated sodium chloride, strong electrolyte. Dilute sodium chloride, weak electrolyte. That's definition number 1 for battery people. Huh? Okay, weak electrolyte, strong electrolyte. But what are they? This is sodium chloride aqueous, this is sodium chloride aqueous. Both of these are sodium chloride aqueous. One is weak, the other is strong. And so the battery person would say, okay, this is a weak electrolyte, this is a strong electrolyte. But our book, the way our book defines it is like this. Our book defines a strong electrolyte as something that completely dissociates into ions. So what happens here in the dilute sodium chloride is this is completely dissociated, but its concentration is very small. Over here, this completely dissociates, although it's not 100% soluble. Do you see I still have some salt crystals here? And so what I've done is I've created what's called a saturated solution. A saturated solution of sodium chloride I can't dissolve an infinite amount. The maximum I can dissolve in 100 milliliters of water should be like this. In 100 milliliters of water, I could dissolve 36 grams. That's called the solubility. This is less than 100 milliliters, so it's less. But to us, both of these are strong electrolytes. They're both strong electrolytes because sodium chloride completely dissociates into ions. It's just one isn't a very good conductor because it's just dilute. Does that make sense? And so we say sodium chloride is a strong electrolyte, but it might not conduct electricity very well. It might not conduct it if there's barely any sodium chloride in there. You know, if there's barely any sodium chloride in there, it's not going to conduct. The more sodium chloride, the more it conducts. So what we're going to do is, we're not working with batteries a lot, and so what we're going to do is we're just going to call sodium chloride aqueous, or sodium chloride in general, a strong electrolyte. Now, solid sodium chloride, does it conduct electricity? No. So one of the problems in chemistry is contamination, cross-contamination. Do you remember a Mono Lake? What was the thing about Mono Lake?
The shrimp seemed to be okay with the acid, isn't that?
The arsenic. Yeah, but there's bacteria thriving in Mono Lake, and the NASA astrobiologists thought that could represent a form of alien life on Earth. You know, it's not that the bacteria came from outer space. It's that, you know, it's just a different. What was it? Rather than phosphorus based, it was arsenic based life. But it turned out that was probably due to cross-contamination. So we try to avoid cross-contamination. And so what I don't want to do is I don't want to contaminate the next thing with sodium chloride. So what we do is we'll just clean the electrodes off here to minimize contamination. I have it unplugged so I don't shock myself. But this is my waste beaker here now. And so let's take a look at what's next. What's next is lead iodide, or actually, is that correct? Lead iodide? I was mistaken. I thought they were going to have the lab set up for us today. Uh-huh. Strong, weak, or non. Since there are two definitions, the usage of electrolyte can be confusing. Some people define it differently than the way you define it. Just be aware of that. And so I don't get too hung up on electrolyte at all because, if you buy sports drinks are full of electrolytes, and they'll define it just as minerals that will help replenish.
An aqueous with sodium chloride, how as a strong or
Strong.
are we getting the observations?
Bright light. There's bright light, no light, and a little bit of light, moderate light or weak light, weakly lit, maybe you would say. Lead iodide. Lead is what we call a heavy metal. Those metals down near the bottom of the periodic table are heavy metals. Heavy metals can interfere with some proteins and screw things up, biologically. And so we try to avoid contact. Like if I open this, I don't want to sneeze in here and create a yellow dust cloud of heavy metal. But these heavy metals, like a lot of these are used in pigments and paint. This is a really pretty color. This is what? Lead 2 iodide. Lead 2 iodide. Lead 4 iodide is not so common, so when people say lead iodide, then it's got to be lead 2, because lead 4 is just not that common, but we still should be careful.
For copper, when we had the metal experiment, with you, it was like a piece of copper, like solid. This is like a powder, is that true? It's like this, what you have in your hand right now.
Powdered copper
It's for lead.
for lead?
They're both solid though.
Yeah, they're both solids. Powdered is fine, it should still conduct. Even if I have powdered copper, which I do, we have powdered copper. I could put powdered copper here and it'll conduct electricity. Just as long as the particles of copper are touching each other, then the electrons can jump from one particle to the other, no problem, as long as they're touching. And the same thing goes with graphite. If I have powdered graphite, it works fine too. In fact, you could buy powdered graphite. People buy it for, I forgot what they call it, but you buy it for electrical contacts to make sure the electrical contact is good. In the old days with the cars, they used to have a little contact switch like this, and you put a little bit of graphite there to improve certain things. But I used to have a bunch of this graphite stuff that I'd use. So I want to handle this very carefully. In fact, if I had nitrile gloves, I'd feel more comfortable. But I don't have them, so just handle it carefully, not to make a mess. I remember, this reminds me, we were using another chemical. I think it was like sodium bismutate. It's also not a very good chemical. It's very reactive. Causes a lot of health issues. So I told people to work with it in the hood. In case they create a dust cloud of it, it'll get sucked into the hood. But this person was working with it on the lab bench, and I look over there, and there's a yellow dust cloud of sodium bismutate there. And they're this engulfed in this yellow dust cloud because they spilled it all over. And I thought, yeah. So you want to be aware of certain things, like sodium chloride, no big deal. That's GRAS. Have you ever heard of GRAS? GRAS, GRAS. You know what the acronym GRAS stands for? GRAS stands for generally regarded as safe. GRAS. This is not GRAS. This is not generally regarded as safe. But sodium chloride is no problem. Do you think it's going to conduct electricity? No. It doesn't conduct electricity. Why?
It's not aqueous.
It doesn't have to be aqueous to conduct electricity. So that's not the reason.
It doesn't have translational mobility.
Yeah, it doesn't have translational mobility. It's locked in a solid state. We can make it aqueous. Lead 2 iodide is what we call insoluble or very, very slightly soluble. Sodium chloride is highly soluble. Did I turn the recording back on? Make sure. Yeah. Sodium chloride is highly soluble because it's 36 grams. But lead isn't very soluble. In 100 milliliters, we can just dissolve a minimal amount. And there's a cutoff. The cutoff is 0.1 moles. If you can dissolve 0.1 moles in a liter, then we'll call it soluble. If you can't dissolve 0.1 moles, then we'll call it insoluble. So we can dissolve less than 0.1 moles in a liter, and therefore this is called insoluble. But a little bit does dissolve. So let's see what happens with a little bit. I'm going to shut off the light here and see if we can see any kind of light coming off this. Yeah, do you see that? This is what we call saturated. It's saturated, meaning no more lead will dissolve. You see all that extra lead-2 iodide on the bottom? It's not dissolving. Yeah.
Does a little SAT in the paper right here, does that mean like slightly soluble?
No, SS means slightly soluble. The little SAT means saturated. That is, you got as much lead as possible to dissolve, and that was it. No more will dissolve. A lot of artists work with lead pigment paint. So artists will sometimes use the gloves and that kind of stuff, just like chemists. But what we should do is proper lab hygiene means washing your hands frequently. Because usually what happens is if you touch some lead-2 iodide and then touch your face or rub your eyes or eat a sandwich, then you can get cross-contamination. That is, you can poison yourself. So what do we call lead? What's happening with lead? Somebody explain it to me. Yeah. Is lead-2 iodide molecular or ionic? Ionic. So it's going to form what type of structure? Lattice. Yeah. And then what happens with that when the lead-2 iodide dissolves?
What if this solid was able to have it, because it had the number and it had the charge, but it didn't have
It has the mu.
the solid?
It has the mu. Mu is very good. So we have an ionic lattice like this. The solid is not going to translate because mu is translational. Zero. So what's happening with PbI2 aqueous is the same thing. The water molecules are going to come in to break apart the lattice. But it's not easy. And so just like sodium chloride, water molecules come in. And they're going to collide with the lattice and try to dissociate it. Okay. These are just water molecules. The water molecules are actually kind of small, but these are kind of exaggerated large. So they're collisions with the water molecules in the lattice, like this. Do you remember molecular dynamics? This process is called dissolution. This is just using quantum mechanics. These quantum mechanics calculations are kind of difficult to do. Ooh, there's one from UCLA. Let's take a look. Oh no, that's not UCLA. It's ucl.ac.uk. Wow. These are painfully slow. I think it's been slowed down, really slow motion. Why is this so slow?
Might be an option to
Can we just get one ion? Just one ion. Without having to listen to the whole musical score. Okay, almost there. Ah. Almost. You have to wait for the crescendo. All right. I can't wait that long. Okay, this is more like it. Okay, there we go. The water molecules are moving so fast, huh? They're blur. This isn't even real time. I'm sure this has been slowed down.
It's for salt, right?
Yeah. This is sodium chloride, I think, in water. So when all of the salt dissolves, then it's not a saturated solution. When we have a saturated solution, we can't dissolve any more salt. But it looks like all the salt dissolves, so we have an unsaturated solution, maybe a saturated solution, but maybe we could dissolve more, maybe we can't dissolve more, but at least all of it dissolved here. And now we see we have translational mobility, and therefore we can conduct electricity. No problem. Here's a sheet of graphite.
some other stuff here.
But what happens with lead 2 iodide is very little of it dissolves. So lead 2 iodide is like video 1. Sodium chloride is like video 2. So with lead 2 iodide is like that. You gotta wait. And then finally we get an ion of lead. And then we gotta wait, and finally we get an ion of chloride, but then it's done, you know? We get so few ions in solution. So that brings up a conflict in the naming of lead 2 iodide. And so what we say is very little dissolves. Very limited solubility. And so most of this stays as solid. But what does dissolve gets split up into ions. And so that little bit that dissolves splits up into aqueous lead ions, and we need 2 iodides for every lead. Aqueous iodide. And so what we end up with is a situation where there's lots of crystal left over. So this is just the crystal that's left over here. And then a little bit of ions. And so in definition 1, for electrolyte, we call it a strong electrolyte. We call it a strong electrolyte because whatever does dissolve is split up into ions here. Can you see this, Blue? Is that visible? I mean, this is... All right. No, I think it's strong electrolyte. Definition 1, strong. So we call it strong electrolyte. Definition 2, it would be a poor conductor of electricity, so it'd be a weak electrolyte. If you're electrochemist, we'd call it a weak electrolyte because it didn't conduct electricity very well. Uh-huh.
So what you're saying is that like the first definition is based on how dissociated.
Right.
And then the second one's based on conductivity.
Right. Exactly. Second one, the electrochemist looks at conductivity only. So we're going to come up with a compromise. What we're going to say is a strong electrolyte but with limited solubility. Limited solubility means N is low, but a strong electrolyte means mu and Z is good. And so the reason it doesn't conduct very well is because of the limited number of ions that form. We're going to go to barium. What do you call that? Barium sulfate. And what I'm going to do is I'm going to talk about something called the solubility rules now. For molecular compounds, It's a very simple solubility rule.
These can be broken, right?
I'm sorry?
Because they're rules, they can break these rules, correct?
They can break easier, break.
Because they're either possibility rules, we can break these rules to that.
Oh, yeah. Rules are not laws. Laws are harder to break. Rules are easier to break. This rule is pretty good. I mean, this might be a law here. Like dissolves like. We'll learn later that oil and water, are they like or are they unlike? They're unlike. And so these are insoluble.
Isn't oil rise and rises to the bottom?
Yeah. Oil, there's some oils that float to the top. There's some oils that sink to the bottom, depending on the density, right?
But they don't mix.
They don't mix, exactly. Alcohol, like let's say ethanol and water are soluble. Sugar and water. You think sugar and water, they aren't so similar, are they? They're totally different, aren't they? But they're similar in certain structural characteristics. And sugar and water are soluble. And it has to do with the structure. Dictates this. Which we're going to cover later, not now. What we're going to cover now are the solubility rules for ionic compounds. I like to use these, but your book has a different set of solubility rules. These are later in chapter something. I'm going to introduce them now. Rule 1, I guess you could say, cations. Group 1 are the alkali metals, and ammonium salts are all soluble.
Ion compounds, cation?
Yeah. So for example, sodium chloride. Soluble or insoluble? Soluble. How about ammonium chloride?
Yes.
Soluble also. What if we have lead 2 chloride? Lead 2 chloride, that's a question mark. It doesn't fit rule 1. So what we have to go on to is rule 2. For rules 2 through 7, we look at the anion. And so the first anions that we look at are nitrates, acetates, and chlorates. What was the formula for nitrate?
Nitrate.
Yes. Good. Nitrates. What's the formula for acetate? Good. And chlorates. What's the formula for chlorate? Good. So nitrates, acetates, and chlorates are all soluble. So, for example, if I had lead 2 nitrate, what's the formula for lead 2 nitrate? Well, I'll take the lead 2 ion and the nitrate, and then what ratio should I mix these together in?
PB, and then NO3.
Good. Is this soluble or insoluble? Soluble. All nitrate salts are soluble. Uh-huh.
Can you move up a little bit? Is the cation the N now? Is that a T or a plus? Yeah.
Up here? Cation here?
No. The NOT.
NOT.
Oh, right next to the word salts.
Oh, it's an H. That's why.
Okay.
For cation group 1, you meant the first group on the periodic table, correct?
Yeah. Group 1 are sodium, or lithium, sodium, potassium, etc. Also H plus would qualify as a group 1.
So I guess it's so long as these ions are in there, it's solid.
Right. Right. So I'm going to do another one. Let's do chromium 3 nitrate or acetate or chlorate. It would be soluble. That's what we predict. Again, these are rules. Okay, what if it's not nitrate, acetate, or chlorate? Then what do? We look at these ions next. Chlorides, bromide. What's the formula for bromide?
BRO.
BRO or BR minus?
BR.
And iodides. Chlorides, bromides, and iodides are all soluble except when paired with silver ion, lead 2 ion, and mercury 1. What was the formula for mercury 1? Hg2, 2 plus. Good. Except when paired with those.
Why is that?
Hmm?
Why is that?
We're not at the why yet.
Okay.
We're just at the observation. The why comes later. Like in science, you come up with the solubility rules first. The why, well, maybe, it's more difficult. And so all we're going to do is we're just observing what we see. And so what does it mean to be insoluble? It doesn't mean it's 100% insoluble. It just means that less than 0.1 moles dissolves in a liter. So let me set the definition over here. Soluble means greater than 0.1 moles dissolves in a liter. This is soluble. SS. SS stands for
Slightly soluble.
slightly soluble. Slightly soluble means it's borderline, so about 0.1 moles dissolves in a liter. We don't talk about grams because if we talk about grams, then it gets more complicated because different atoms weigh different amounts. So moles is a little bit more better in the sense that we can visualize it via atoms or moles of atoms dissolving. So we have S, which is soluble. We have SS, which is slightly soluble. And what was the last designation? I, which is insoluble.
So less than 1 mole.
What?
Less than 1 mole.
Yes. Less than 0.1 moles. It's arbitrary. Who came up with 0.1 moles? Totally arbitrary. Dissolves in a liter. But somebody had to come up with a cutoff, so whoever did it, it's fine. So we saw that lead 2, PbI2 is S, SS, or I?
S. Okay.
I. PbI2 is insoluble, which means just a tiny bit dissolved, if at all. How about when Ag is paired with nitrate? This is called silver nitrate. Is that S or I or SS?
S.
This is soluble. Nitrate salts are soluble. How about this one? Hg2, Cl2. Insoluble. In I. Well, what if it's not one of these ions, chloride, bromide, and iodide? Then we look at the next one. Next one will be sulfates. What was the formula for sulfate?
SO4 minus 2 minus.
So what we say are sulfates are soluble. Oops. Except when paired with silver, lead 2, mercury 1. What's the formula for mercury 2? Calcium? What's the charge on calcium? Strontium? And barium. Silver, I'm going to put a little asterisk here, because it's SS. So PbSO4, what do we call that? PbSO4 would be called lead 2 sulfate. Is it soluble or insoluble? It is insoluble, correct. What do we call this? MnSO4. Did, MnSO4 is called, no, close. No, magnesium is Mg. Mn is manganese. Manganese is correct, But there's a problem with it.
Number 2.
Yes. Manganese is +2 +3. We got to indicate which one. This is manganese +2. Is this soluble or insoluble?
Soluble.
This is soluble. How about manganese 3? Manganese 3 is a bit more complex. So if I have manganese in the +3 and a sulfate in the -2, what's the ratio of ions? We could use the cross multiplication. Remember the cross multiplication I did yesterday?
Manganese 2, 2,
Yes.
sulfate 3.
Yes. Good. It's going to be manganese with 2 of those and a sulfate with 3 of these. And this is going to be called what?
Manganese 2 trisulfate.
No.
Manganese.
Come on. Manganese, what did you call it? Did you call it dimanganese trisulfate? We use dimanganese trisulfate for binary molecular compounds. This is an ionic compound, so we named the cation. What's the name of the cation?
Manganese 2. And it's sulfate.
Manganese, not 2, manganese 3.
Trisulfate.
We don't use tri. We don't use tri because we could easily figure it out based on charge.
Sulfate.
Yes. We only use the tri when we're dealing with the binary moleculars. And so it's just called manganese 3 sulfate. And we could figure it out here because manganese 3 is this and sulfate is this. And so we could easily figure out what the ratio is based on the charge balancing. So we don't need to use the prefix tri. But we have to use the prefix here, like CO versus CO2. We can't call these both carbon oxide, right?
Carbon dioxide.
One's called carbon dioxide, the other's called carbon monoxide. That's because carbon's variable charge. It could be 2 or it could be 4. If we call this carbon 2 oxide, fine. If we call that carbon 4 oxide, that works. But if we don't use carbon 2 and carbon 4, then we have to use mono and di. Manganese 3 sulfate, soluble, insoluble, slightly soluble? Soluble. It's only when sulfate is paired with these cations we call it insoluble. Name this one for me. Uh-huh.
Besides barium, what was the other element starting with B?
There are none other here.
Which one's that one? Bromine?
No, barium. Ba2+. What's the name of this? Calcium 2 sulfate or just calcium sulfate? Calcium 2 sulfate? What are the common charges for calcium?
It's just 2.
Is it just 2 or 1 and 2? Sulfate is only one charge, right? 2 minus? What about calcium? Is calcium variable charge or a fixed charge? Calcium's fixed charge. So there's only one charge on calcium.
There's calcium sulfate.
So it's just calcium sulfate. Soluble, insoluble, slightly soluble? Insoluble. It's one of the exceptions. Most sulfates are soluble, except for these 7. What's the formula for hydroxide?
OH negative.
Now we shift.
The acids.
No, are insoluble. Hydroxides are insoluble. So most hydroxides are insoluble, except when paired with group 1, ammonium, calcium, strontium, and barium. What is this called? Sodium hydroxide has other names. Have you heard of lye? Have you heard of drain cleaner? If you go to the supermarket, you can buy sodium hydroxide. But it's marked poisonous. You don't want to eat it. Is sodium hydroxide soluble or insoluble?
Soluble.
Let's say you go to the supermarket, your drain is clogged, you're looking for drain cleaner, but they're all out of stock. There's no more drain cleaner on the shelf. So then you walk down the aisle and you start reading the ingredients of all the other stuff they have in the supermarket, and then you come across something that they have. And they have something called milk of magnesia. Have you heard of milk of magnesia? Yeah, they have milk of magnesia in the other section. And it contains this. What is this called?
Manganese.
It's not manganese, because manganese would be Mn. This is Mg.
Manganese.
Magnesium. Magnesium 2. Magnesium Roman numeral 2, or just magnesium? Why just magnesium?
Fixed charge.
It's fixed charge.
Hydroxide.
Magnesium hydroxide. So you search the aisles and then you find milk of magnesia and you look at the ingredients. Milk of magnesia contains magnesium hydroxide. And you go, okay, I'm going to use milk of magnesia to clean my drain. Is it going to be very effective?
No.
Now, what is the solubility of magnesium hydroxide?
Soluble.
Insoluble, soluble, slightly soluble?
Insoluble.
Insoluble. What you need to clean the drains is hydroxide. Hydroxide attacks fats, breaks them up, and hair, and other stuff that might clog the drain. But if it's magnesium hydroxide, is there much hydroxide that breaks off the magnesium hydroxide crystal? You gonna have very many ions in there? No. So do you think magnesium hydroxide would be a very effective drain cleaner? No. It wouldn't be very effective, right? We call sodium hydroxide a strong base. However, it's a base because of the hydroxide. Sodium is not a big deal. We eat sodium. Lots of people eat sodium. A lot of people like the taste of sodium. I like the taste of sodium. Chloride doesn't have any taste, though. Chlorine does. However, magnesium hydroxide is not considered a strong base. It's considered a weak base. But isn't that kind of weird? Because look how much more hydroxide there is. Look at the ratio of hydroxide. How many hydroxides are there? Two hydroxides for every magnesium. And if you look at sodium hydroxide, how many hydroxides do we have there?
One.
Just one. Shouldn't magnesium hydroxide be a stronger base? Shouldn't that be an even more powerful drain cleaner? Bases work good. Typical bases are slippery. It's one of the, like soap, soaps are bases. Soaps work good at cleaning. So why do you think magnesium hydroxide is classed as a weak base, but sodium hydroxide is classed as a strong base? It has to do because of its
The number of properties?
It has to do strictly with its solubility. Have you ever had a CAT scan? A CAT scan, they make you drink heavy metal. Do you know they make you drink heavy metal? You know what heavy metal they make you drink in a CAT scan? They make you drink barium. Barium is a heavy metal. It's toxic. However, I've had it. I've drank in the cocktail. The cocktail is barium sulfate, I think. It's a barium sulfate. Is barium sulfate soluble or insoluble?
Barium sulfate?
Yeah.
Insoluble.
Barium sulfate's insoluble. How about barium chloride? What's the formula for barium chloride?
BaCl2.
Is that soluble or insoluble? It's soluble. If you go in for a CAT scan and they run out of barium sulfate cocktail and they want to replace it with barium chloride cocktail, don't drink it. Why not? Because barium chloride is soluble and they're going to have lots of barium ions that can, the heavy metals, what they do to the proteins, they'll interact with the proteins and cause them to not function properly. Right? Especially sulfur-containing proteins. Some of them. Although barium might be okay. I don't know the exact mechanism. But you can drink this stuff. Why can you drink this stuff? It's insoluble, so it gets in your stomach. It would be a problem if it gets in your stomach and the acid breaks it apart. But it doesn't. Whereas don't drink this stuff.
I said you tried it before, right?
I've drank it before. I've drank it before. And then I had another imaging. Maybe it was a CAT scan. I don't remember what it was. It was another imaging where they want to use heavy metals. They want to use heavy metals in CAT scans because X-rays interact with electrons. Barium has lots of electrons. And so they replaced it with iodine. So I didn't have a reaction with the barium sulfate, but I did have a reaction with iodine. And a slight allergic reaction to the iodine. Iodine also has a lot of electrons. And what's that? The barium sulfate? Tasted like paste, like milk of magnesia type paste, chalk, a suspension of chalk. You take some chalkboard chalk and chew on it, or rock, you take some crushed powdered rock, like limestone or something like that and chew on it. That's what it tasted like. It didn't taste bad. It's fine. All right, so I'm going to reverse the story. You know what they use milk of magnesia for?
Drinking. Medicine.
Milk of magnesia is not very soluble, so it's a laxative, and it tastes like paste. I think it's not very good. The taste is bad. I don't like the taste of it, but it's a laxative. Let's say you go to the supermarket and they're out of milk of magnesia, but they do have drain cleaner. Should you use the drain cleaner instead of the milk of magnesia?
Yes, you gotta creep it out, that was great.
Yeah?
It's like real. That must like be there, like really bothering you. You really got like you're out of it. Go ahead.
Yeah. No, and why not? I mean, yeah, there's no way. It would just be the reverse. So we worry about heavy metals. Like barium, maybe that's okay, but would you want to drink a lead cocktail? Not really. Lead is excellent at absorbing X-rays because it's got a lot of electrons. So if you go to the dentist, they put the lead apron on you and whatever. But you don't really want to drink lead cocktail because of heavy metal poisoning. And then paint pigment, white lead used to make a brilliant white pigment in paint. And so a lot of old houses have lead paints in them.
Like taste sweet or something.
Hmm?
Does it taste sweet or something?
I don't know what it tastes like because I've never eaten it, but little kids will eat the paint off the walls, and then they'll get high lead concentration. Not only that, some old communities, you know what they use for the pipes? Like in the Roman times, they use this too. They use lead pipes. So there are still houses that have lead pipes in them. Lead is actually pretty good for pipes. But the problem is the lead leaches out into the water and will cause heavy metal poisoning. So, do you know that this will be a little side topic, but let me come back to this little side topic after I finish this here. So that was 5. 6, sulfides. What's the formula for sulfide with a D? S2 minus. Good. Sulfides are insoluble in water, except group 1, ammonium, and group 2. And so an example of this would be this. MgS is called
Magnesium sulfide.
Yeah, this one's called magnesium sulfide. How about MnS? What do we call MnS? Manganese?
Sulfide.
Close. Yeah, manganese, Roman numeral 2, sulfide.
So manganese is 2 and 3 charges. Magnesium is a fixed charge.
Yes. Is manganese soluble or insoluble? Let's start with manganese first.
Manganese is insoluble.
Insoluble. How about magnesium? Insoluble? or soluble? Soluble. All right, the last set of rules deal with carbonate. What's the formula for carbonate? Chromate?
CrO4 negative.
Is that correct?
2 minus.
Yeah. 2 minus. The only 1 minus 1 is the permanganate with the metal. And acetate, permanganate, acetate. Carbonates, chromates, and phosphate. What's the formula for phosphate?
FO4 3 minus.
What is it? F?
E.
P?
EO4 3 minus.
That's correct. Are all insoluble except group 1 and ammonium. What's the formula for ammonium phosphate?
Ammonium phosphate.
Yeah.
NH4 3 and EO4.
That's correct. Is it soluble or insoluble? Soluble is correct. What's the formula for mercury 1 phosphate?
Mercury 1 phosphate.
That one's going to be a bit more tricky.
Isn't it?
So we're going to do Hg 2, 2 plus,
And then EO4 negative.
and then we're just going to do the cross multiplication deal just to make our life a little bit easier. But it's going to look weird because it's going to be how many mercury 1s? 3. So this looks kind of weird. And how many phosphates? 2. So it's a strange looking formula, but that would be it. Is it soluble or insoluble?
Insoluble.
Insoluble.
Also, on the mercury, could you scroll up a little bit? The mercury right there, did you mean to put Hg just only +1?
No.
It's 2 plus?
Yes.
Gotcha.
2, Hg2, 2 plus.
Yeah.
All right, those are the solubility rules. Let me ask you some questions. We're going to go back and do you know there's some drugs for treating heavy metal poisoning? There's an anion called EDTA. And it's 4 minus. The whole formula is kind of long, so we don't write out the whole formula. I could write it out. The EDTA's got a pretty big structure. And EDTA likes metal ions. So let me ask you this. What would be a more effective drain cleaner? Sodium hydroxide or magnesium hydroxide? Sodium hydroxide, more effective drain cleaner. So, what would be a more effective EDTA agent? We could have sodium EDTA versus calcium EDTA. Which would be more aggressive, which would be less aggressive drug?
Sodium more aggressive.
Sodium EDTA would be the more aggressive drug. And calcium EDTA should be the less aggressive. And how did you come up with that conclusion?
Based on sodium hydroxide.
Yeah, based on this, freeing up. It's the EDTA that needs to be free. And if the EDTA is stuck on calcium, then it's going to be less free. And if you look at the solubility rules, do you see a pattern? The pattern here is the higher the charge, the less soluble. The higher the charge, the stronger the lattice. The stronger the Coulombic force of attraction. And so I just want to finish with this. Sodium EDTA is for acute poisoning. Something that's severe, it needs to be taken down immediately. And so something as simple as solubility rules can this is called chelation therapy. Let's see if I can get this to fit in here. These are called chelating agents. Chelating agents bind lead in soft tissues and are used in treatment of lead poisoning. So the two common chelating agents are calcium EDTA, which is shown here, and sodium EDTA, which is shown here. Sodium EDTA is more aggressive and is not administered to children. It's more for acute, and it's for adults. Sodium EDTA contains a warning statement. The use of this drug in any particular patient is recommended only when the severity of the clinical condition justifies the aggressive measures with this type of therapy. So sodium TA is more aggressive. So here's a case study here. In 2005, the Texas Department of Health reported this. February 2005, a girl aged 2 years who was tested for blood lead during routine health surveillance had a capillary blood lead level of 47 micrograms per deciliter. A venous VLL of 48 micrograms per deciliter obtained 12 days later confirmed elevated BLL. So the patient went in for chelation therapy. So medication order was given to give calcium EDTA intravenous IV. At 4 p.m. on the day of admission, the patient received her first dose of intravenous calcium EDTA. At 4:35, she was administered 200 milligrams of oral Siximmer. Her vital signs remained normal throughout the night. At 4 a.m. the next day, a dose of sodium EDTA instead of calcium EDTA was administered. An hour later, the patient's serum calcium had decreased to 5.2, normal value 8.5 to 10.5. At 7:05 a.m., the child's mother noticed that the child was limp and not breathing. Bedside procedures did not restore normal cardiac rhythm, and cardiac resuscitation code was called at 7:25 a.m. The child had no palpable audible heartbeat, repeat laboratory values, etc., and the girl was pronounced dead at 8:12 a.m. So she checked into the hospital 4 p.m., was dead by 8:12 a.m. the next day. 2 years old. Can you believe that? It was a mistake. It was a mistake. Rather than grabbing the calcium EDTA, they accidentally grabbed the sodium EDTA, not knowing that there's a difference. Okay. Anyway, let's. Well, that's not the only one. 5-year-old boy, 53-year-old. And a bunch more. Can you believe that? All from grabbing the wrong bottle of EDTA. So you got to watch out. Anyway, CDC's recommended to discontinue carrying sodium EDTA to prevent it.